Welcome. In this session in linear data analysis, we'll explore the use of an artificial neuron that has a logistic activation function, and we'll explore it with using some familiar data. We'll use Fisher's iris data, and in particular, we'll use the petal data. So these are two measurements of each flower. There were 150 flowers that were measured, and they measured the petal length and the petal width. We're going to label the type B, or beachhead plant, or Iris setosa, as having a label 1, and we'll label the other types, which are two species that are both purple, we'll assign those as label 0. When we plot these data, this is what we get. Here we have the petal length in centimeters as the horizontal axis and the petal width as the vertical axis. These cyan plus signs are the type B, or beachhead plants, and these red circles are the purple plants. What we can see is these are forming two visual clusters, and there's one flower that has an almost anomalous petal measurement. What can we do? Well, if I use the squared error objective, this is the hyperplane that I calculate. And so what I did was I implemented a numerical solver. And what I'm showing here is I'm showing the results of taking a unit normal with the dot product of a new vector that I'm scoring, and then I'm adding a bias scalar. And let's observe that it's computing. What it's computing is actually a weight vector W, the dot product with the data vector that we're scoring, and a general bias term. So this is what happens when I perform my numerical simulation to find the separating hyperplane. If I use MATLAB's GLM fit function, it will do logistic regression. And in this case, what I'm doing is I'm showing you its unit normal and the associated bias term. What's the difference between these? Well, they're both separating the data, and they're doing it in a very slightly different way. Now, let's try visualizing these scores. If I look at my squared objective, what I see is that the largest positive score is slightly greater than 10, and the largest negative score is slightly less than -30. This is one way to represent it, and what's happened is that the hyperplane is producing scores so that 0 is the decision of whether a data vector is on the positive side of the hyperplane or is not. Another way that I can visualize this is I can give these data a vertical axis according to that label, which is 0 or 1. When I do that, what I see is these are the scores, so they're still ranging from -30 as the most negative to a little more than +10 as the most positive. And now what I've done is, if they have a label of 0, I'm putting them at the 0 height, and if they have a label of 1, I'm putting them at the 1 height. If I now take each of these scores and I compute the logistic function, this is what I see, is that it's got a fairly smooth appearance to it, and this, as it works out, corresponds to the way that the squared error worked. If we recall in the previous session, the squared error for the squared error objective was a maximum of 1, and what that does is it never really strongly penalizes these points that are far away from the proposed hyperplane. Now, I could also use MATLAB's GLM fit to do a logistic regression. When I do that, I'm also getting a separation around 0, which is what we should see. Let's now look at these numerical values. Is that this numerical value is not quite 100, and this is almost 200. So these are not exactly a factor of 10 different, but they're really, really different. So what's happening is when I show you what the separating hyperplanes look like, I'm showing you using the unit normals, but what is happening is that the computation is using these unrestricted values. And when I then plot these data with a vertical value that corresponds to the label, what I see is that these are all all have label 0, these all have label 1, so they're all correctly classified. Our accuracy is 100%. If I now plot the logistic function's response to each of these scores, what I see is that it's taking almost a step. And this almost step function corresponds to the way that the negative log error is severely penalizing these outliers. And indeed, when I ran this, MATLAB was complaining, it was giving me a warning, saying that the ideal weight vector actually had infinite weights. So, what have we got in this session so far? Well, we now understand a need for nonlinear classification. We recognize that it requires numerical solution that goes beyond what we do in linear data analysis, so this is a bridge to other areas of machine learning. And there are multiple conceptual frameworks that we can look at. What we explored here was the squared error objective and the negative log objective. The choice of the objective function and indeed the activation function itself depends strongly on the data that you're provided with and the eventual use of your data. So, what have we learned in this session? Well, we're now able to determine whether data might be linearly separable. We can do that by in 2 dimensions by plotting, and in higher dimensions by using our score plots. We can use library functions to compute the scores, in particular for the logistic regression. And we can assess the results using accuracy, visual methods, or other methods that are appropriate for our data.